Hello, this is Don Parr with Zaxis. We welcome you to our session today. Um, Zaxis has been in leak testing since the 80s. We test a variety of products for a variety of companies around the world. Today we'll be discussing kind of a leak test 101. There will be myself, Don Parr, Charlie Bright, and Doug Harding. Charlie and I are in sales, and Doug is the manager of our technical support team. We look forward to the meeting.
Once again, if you have questions, use the Q&A tool. So, all right. So what is a leak test? A lot of people new to leak testing want to know what a leak test is. It's a process to verify that a part won't leak fluid in or out. So there are different kinds of products. There's electronics and other devices where getting water into your part could be detrimental to the use of the part. And then there are other products that you want to keep the water in. Both of those types of testing are what we're going to talk about as we go throughout this discussion today. So if we put it in real basic terms, if you suspect that your car has a leak in the tire, you'd want to check that by using a pressure gauge. So you would take a pressure gauge, you'd measure the pressure, and then you'd come back a period of time later to determine if your tire has a flat. So that is what Z-axis does. We use compressed air, and we look with a high resolution sensor, and we monitor for decay in pressure. And so what is a leak? We take a test volume. We always use air, and then we look for a volume of air to leak out of that volume. That air leaving the test volume creates a drop in pressure or a decay. So that's why it's called pressure decay. So the real basics of how we perform a pressure decay, you take your air in from your house air supply, it goes to a regulator. That regulator then steps it down to a pressure that you want to measure at. And then we have a couple of valves that are used to fill and then isolate the part from the supply. And then we use that transducer to measure the decay in your product. So if we look at the graph of what this looks like, and we'll go into more detail, the green line represents the pressure inside of your part. So we fill to a pressure, we shut off the valves, we settle or stabilize, then we monitor during the test, and then we vent the air out of the part. So if we look at the parameters that are set for both a pressure decay and vacuum decay, they use the same parameters. One uses positive pressure, one uses vacuum pressure. So we first have a test pressure, and we're going to be talking a little bit more about these as we get going, but so we have a test pressure, and then we have tolerances that are allowed. As long as you fall between the tolerances, then the test will continue. So for the test, we have a fill time, and this is the amount of time that we open the valves so that we can fill your part up with pressure. At the end of the fill time, we shut those valves, we allow the part to settle, and during the settle time, we just account for, there's thermodynamics, there's some elasticity or physics of the part that we accommodate with that settle time. Doug will be talking about that a little bit later, but then we move on to the test time. The test time is how much time you allow to monitor and look for a decay. And then we have the vent time, which allows you to vent the time. And then we have a reject level. This is how much is allowed to decay during the test. If it decays less than your reject level, the part will pass. So now if we look at that graph again, and we start applying the limits to that graph. During fill, we have our plus and minus tolerances, as long as the green line, fast fingers, as long as your pressure stays between the tolerances, then you will continue to the next step. During the settle, we use those same tolerances. If it falls below that below the minimum tolerance or the minus tolerance of test pressure, it will give you a gross leak. So I've noted on this chart here, you've got the high pressure, low pressure, and gross leak. Anytime you fall outside of those boundaries, you're going to get a failure, and those are the failures that'll show up on the screen. Then we get to test, and we have the decay limit, how much decay is allowed. If you drop below that decay limit, then you'll get a leak failure. So this shows on the screen, this shows what limits we apply to that pressure curve. On the tester, all of these settings are adjusted using the touchscreen. The gray fields are fields that are editable, so you can adjust the test pressure, the tolerances. We look at the fixturing. There's some tooling allowed in the tester, and we can be talking about these in later discussions, or if you have questions, we can follow up with you more on how the fixturing works. This is the limits screen. So this is where you set all of those timers and the reject limit. So all of these are done, you know, it is a touch screen. The gray fields are editable. Before I move on, I noticed that Mike has asked, what's the lowest leak rate that is detectable? It kind of depends on the product and the size. Typically, when you're looking, your question specifically is what is the lowest air leak test as opposed to tracer leak gas? Tracer leak is typically 1 × 10⁻⁴ or more. 1 × 10⁻³ is about the limit we do, but that all depends on the product and the size, and there's a few things we'll talk a little bit about, but yeah, 1 × 10⁻³ per second is about as low as you'd ever try to go with a pressure decay test. So, yep, cc's per minute, I see that. All right, so now if we go and we look at the tester running, we'll see, we're going to start the test. You're going to see the line drawing on the screen. And then this is a close-up of it drawing on the screen. So you can see the tester running a test and performing all those. One note that I'll make, and I'll back up a couple of slides here and just show the red lines on this chart represent inside of the red lines or what you see on the screen. So during fill and settle, the top of the screen is your plus tolerance, the bottom of the screen is your minus tolerance, and the middle is your test pressure. And then when you get to test, you're only, the top of the screen is the beginning pressure and the bottom of the screen is that decay limit. So while it may look like on that video, the pressure is jumping up, we're just changing the resolution of the screen so that you can zoom in and see what's actually happening. Get back to where I was. So the next part we're going to talk about is how long do you test for? And that all kind of varies on what the part is. Sometimes there's a specification that's been around for the product within your company. Sometimes you test to an ISO or an ASTM standard. All of those will dictate how long you test for, what the leak rate is that you're looking for, because it varies by the product, the use. And so to help us understand leak rate, we look at here at the screen, we look here, we've got delta P is the decay in pressure, V is the volume, the delta T is the test time. That's just the time during the test, not fill settle. So it's just the test time, and then atmospheric pressure. So if we take this equation, we can convert that decay in pressure into a volumetric cc per minute. So let me just, we will continue on. So if we look at the leak rate, 0.02. So if we plug in the values here, then we can determine a 0.02 psi in 0.05 minutes is equal to 1.36 cc's. So if we apply those numbers in there, we can calculate the cc per minute. So the next section, Doug's going to take some time and talk about setting up test timers and how to set those limits. So Doug will be taking over. I'm running the PowerPoint, so when you need the next slide, holler, Doug.
So there are two main issues we run into with leak testing. Making a repeatable, accurate, sensitive test. Those are factors that are because of the physics of what's going on. The two main factors we deal with are the thermodynamics of compressing air into a set volume, and the second is elastomeric creep, sometimes called compliance or stretch. These two things can be nullified out to the point where when we see a decay on the screen, it indicates a decay of actual air leaving the part, being an actual leak, not because of these two other physical factors. So the ideal gas law tells us that as we increase the pressure in a set volume, we also increase its temperature. Once we've filled that to a specific pressure, we now allow for nature to take its course, and that temperature then comes back to equilibrium through the media of the part. One way I like to give you an example to think about is the picture shown on the screen is, let's take a glass jar, a big mason jar, and let's pretend that that is our test part. That's the part we're going to be testing. And if I took some marbles, which would then represent the air molecules, and as I began to fill the jar full of marbles, every time a marble hits the jar or hits another marble, we get a loud clanking sound. And the more I jam into the jar, the faster I do that, the more each marble hits the jar, the more marbles hit each other. Those would represent the molecules of air hitting each other and hitting the part. But when they do that, they're actually causing friction and causing heat. A very small amount. It's not something that we could measure easily, but they're adding heat to the system. So once the jar of marbles is full, we now allow some time for that heat to come back to equilibrium. If we didn't allow for any time for that to come back to equilibrium, we would see the effects of that. And we can see that because of the ideal gas law, we could see what happened. I actually have a slide coming up that will actually show you numerically what that effect is. And you can see that on any test with any part. You can see the effects of the thermodynamic process happening in these slides. The other thing I'd like to go back, the previous slide also has an example that's easy to understand of elastomeric creep, and that's the party balloon. Compliance or stretch or part movement will also play a part in understanding where we want to set our test times. Because if you take a party balloon and you blow that party balloon up the first time, you about blow your eardrums out because it has a lot of breakaway force for it to begin to fill. But once you do fill it, the volume expands. So the pressure in the balloon stays fairly similar, but the volume changes. So as I add more pressure, the volume expands and we come back to an equilibrium of pressure. So the pressure stays very close to where it will be. Once you get to its stretching point or past that point, it will try to stop stretching, or it will at least have some movement. And when it tries to stop, at that point, we can then measure to see if there's any changes. So if you have a softer part or parts maybe with seals or a balloon or maybe it's a bag or something else, that volume change while the test is occurring is going to show up later in the test step when we actually start watching for very small changes in pressure. because we have such great resolution, either a change in volume or a change in temperature shows up on the screen of the tester as a change in pressure. Now, just because the screen shows you a number doesn't necessarily mean that you have actual air leaking out of the product. It might mean you have one or the other of these two elements happening, either the thermodynamics or the compliance of your part. One way to check for that is to actually just modify your test time slightly to see what happens. So if we go to the next slide, what I did is I took a part that we had here. That was actually, it's about a 125 milliliter part, and I tested it at 10 psi pressure, and all I did was I chose some times. And in this case, I chose you can see on the bottom, I chose a fill time of 1 second, and then 2 seconds, then 3 seconds, then 4 seconds. And I kept the settle time at 2 seconds and the test time at 3 seconds across all of this. So all I did was change the fill time. And the results you see on the screen are actually the decay values at the end of the test. You can see they made a difference by how much fill time I had. You can see that the results actually get smaller and smaller. Now this was the same part, was tested on a 2-minute interval in between. So I let the part come back to equilibrium as far as the physical size and the temperature back to ambient. But with a 1 second fill time, you can see with just what I'm calling a nominal decay, or this part was expected to be a good part, we get a decay close to 0.05 psi. I then ran 2 minutes later, ran that part again with a known leak or a leak standard at a specified rate. In this case, it was about a 0.5 cc leak rate at 10 psi. And you can see the orange line, then with the leak, I get a decay of about 0.09 psi. So pretty good. I can see a difference between a good and a bad. But the difference during this 1 second of fill, I only get about a 1.8 times difference between a good part and a bad part. One of the kind of rule of thumbs that we've used for years is a good place to make sure you have a good, repeatable, sensitive test is to have about a 3x or a 3 times differential between a good part and a part that is either leaking at your spec or has your known manufacturing defect. So even though we see a separation between that, and this is only a sample of one, it might be a good test, but we might want to make it better. So in the second test, I added a second to the fill time. So now I have 2 seconds of fill, 2 seconds of settle, and 3 seconds of test. And you can see my nominal decay of the good part, it actually went down. Now that's because I had another second for the thermodynamics to calm down. I had another second for the compliance to calm down. And because the part wasn't moving and the temperature wasn't changing as much, when I actually get to my test step, the decay is a little lower. Now this hasn't changed. The part didn't leak less. I didn't seal it in any way. But you can see now that the differential between a good part and a bad part has now increased to about 2.3 times. So we're getting closer and closer to what would be a very repeatable, highly repeatable test by adding a mere second to the time. Again, with the third test, I added a total of 3 seconds to the fill time, and you can see again the nominal decay drops. The part with the actual known leak rate, the differential between that increases to 3.5. At this point, I would say that would be a very good test, a great place to start running some gauge R&R on to prove that your process is capable, I would start running on 20 to 30 part pieces so I can get some statistical analysis on it. But this is about where I'd want that test to be. So I would have a 3-second fill, a 2-second settle, and a 3-second test. You can see if I do add another second, we continue to see a growth in the differential between a good part and a bad part. This one being about 5.9 times, where the nominal part is going to be a very small number, and the part with the actual manufacturing defect is a larger number. Now there will come a diminishing return, just because I can add 1 second or 2 seconds. There will be a point where adding a couple seconds won't really get you any more separation. There are other things that we can start to think about to get more separation after that. But what we've really done here by affecting the fill time is to reduce that thermodynamic or elastomeric creep so that it's nullified to the point where we can really see air leaving the part because of a manufacturing defect and not because of a thermodynamic or compliant change in the part. If at this point we've added some time and we still don't see as much separation as we like to have, well, now we have 2 other steps that can help us out. And if the differential between a good part and a bad part are not large enough, we could simply add some test step time to get those 2 numbers to start to separate. There's a question.
So Jennifer has asked if, I'm going to talk a little bit about fill pressure here coming up in a little bit, but Jennifer's question was, how long do you know how long, how do you determine how long to settle for?
Okay, so settle is kind of a step that is in there to help us transition things. I would recommend you would have more time in the fill step. The settle might only need to be 1 or 2 seconds long, just enough time for valves to close and any ringing that might occur because of an actual valve shutting and moving. There's not a real need to have a lot of settle time if you have enough fill time. In the good rule of thumb I always say to start with is, when we get asked how much fill time do I really need, is the minimum we recommend is whatever time it takes to get your product to pressure plus 1 second. And that's a great place to start because it allows the part to do what I call soak. We want to get to pressure, but we want to allow for any compliant, any movement or stretch of that to occur. Some parts might have kind of a tortured path to fill through, where the air might need to find its way through a smaller orifice or a small tube. So if you initially fill and it immediately goes to fill very quickly and you have a tortured path, it might not be a fair fill step because it's still trying to make its way into the rest of the part. And you'll see that by, if you had a very short fill time, once you went to the settle step, the pressure might drop quite a bit, and that indicates that the part was still being filled through that tortured path. When we actually fill the product, we're filling through a set regulator in the machine. We have 2 options that we can do, either a manual regulator or an electronic regulator. The majority of the units will have the manual regulator, which is a standard option. We set the test pressure by simply blocking the test port, either with a part or with your thumb if the pressure is low enough. And in the system, we can turn the valves that will allow air to go through the system and pass the pressure sensor. Once that's live and running, you can just simply turn a dial and watch a reading on the screen so that it will get to your achieved test pressure. So in this case, it was 10. So I blocked the port with my thumb and then turn the dial on the, excuse me, the regulator until the readout read 10 PSI. Then I knew the regulator was physically set in place in the case of a manual regulator. If it was an electronic regulator, and those models all would have an A in the model part number, it's simply a matter of just entering the value that you wanted to go to. If it was 10, you would enter 10. If it was 2.5, you entered 2.5. And based on the calibration and the function of the machine, it would automatically go to that test pressure.
So I think one of the other questions that Jennifer, and I'm going to guess here, is she's asking how to set fill pressure. And we talk a little bit more about that coming up, but it depends on the use of the product. So I don't know, Doug, did you want to continue? Did you cover what you needed to on that slide before we move on?
Yeah, if there are any other questions, you know, you can put them into the Q&A, and I'll just keep monitoring that while Don goes on. Or if you have other questions, you can contact us offline as well.
Okay. So we'll talk a little bit more, Jennifer, about fill pressure. Zach has asked if the higher the pressure, the more the fill time. Typically, yep, it will take a little bit more time to get to a higher pressure than it does a lower pressure. Naval has asked a little bit about why is there more pressure decay in a first part run compared to a second part run. So Doug, do you want to talk a little bit about that elasticity and repeating a test, retesting?
Sure. Let's go back to my example of the party balloon. Think of the last time you blew a balloon up. The first time it was very difficult because it had that initial stretch you had to get over. Well, if you let the air out of it and then try and blow it up again the second time, it's a little easier because you've taken some of the stretch out of that balloon the first time. So normally when we test products on the manufacturing line, you only get the first shot. The first shot is what we'll refer to as a virgin test. But if you're doing some setup and some repeatability testing, if you did run the test multiple times back to back, you would find that the results for that part would get better and better and better, because what you've done is you've stretched it to a point where in that finite set amount of time, so let's say for example you had the 3 seconds of fill. The first time you test it, you give it that 3 seconds to continue to expand and get to a certain point. Well, when you vent it and the part collapses again, if you test it again after that, it immediately goes to the size that it was. It doesn't have to fight that stretch and grow at a slow rate. And so because it immediately got to the size, it now has more time to soak. You are at pressure for longer. So now we're canceling out more thermodynamics, we're canceling out more compliance. So now when it goes into the test, you'll see less of a decay because of the compliance and because of the thermodynamics being nullified out. And you can prove that on any product, any part, simply by running the part 3 times back to back to back. You will get reduced decays. But if you're trying to do some setup and or some repeatability testing, what we usually recommend is having multiple parts to test. But if you don't have that many parts that you can test, we recommend wait at least 2 minutes. So remove the part from being tested and let it sit for 2 minutes. It will come back to ambient temperature. It will try to return to close to what the virgin shape would be, and you'll get more of a repeatability. But if you had 10 or 20 or 30 parts, you could start running each test, and by the time you came back to the first one to do repeatability, it would be back to more as what you would expect the first time. So it's a common thing that will happen if you test it part multiple times.
All right, so we'll move to the next slide. We're and then this will address a little bit more of Jennifer's question about fill pressures. So when you're looking at testing a part, it's always good to know what's the end use of the product. How is it going to be used? What pressure is it going to experience during its use? What is the purpose of the part? And what is the purpose of the test? Are we keeping water in? Are we keeping water out? And then it's good to understand the difference between air and liquid. Air is smaller than liquid, so you'll get more air decay than you would a liquid decay. So the next slide talks a little bit about a falling drop of water. ISO 10555 is an ISO standard for catheter testing. The spec calls out that you pressurize the part with hydraulic pressure, water pressure to 45 psi, and so you pressurize it to 45 psi, a drop of water cannot form on the outside of the part and fall off in less than 30 seconds. So this is a test that most catheter manufacturers try to do on their product. So we worked with the customer to develop limits. So we had that spec, we had their product, and together we worked on how to do that. So we took their product and we, with them, worked with a company to laser drill holes from 2 to 20 microns in diameter. And then we began doing our testing. I'll make a note that you do all of your air testing first. No matter how hard you try and how good you think you are, you will have water or residue left in the part. So the last thing you want to do to the product is put water in it, because once the water's been in it, it won't test the same with air again. So what we did with this customer is we drilled all of these parts, we did flow tests, we did a pressure decay test, and then the last step is we filled it full of water and we did the water test. And as you can see on the screen, at the 8 micron hole, 8.07 micron, a falling drop of water took 2 minutes and 25 seconds to form. And when we did a flow test on that hole was about 0.855. So then we moved out to 8.34. It took 1 minute and 41 seconds for the time to fall, or for the drop to fall, 0.58 cc's. So then you can see the curve. Eventually, we got to where it was about a 2 cc per minute leak. It was a 10 micron hole. And that was the equivalent of the leak, the falling drop of water for this ISO test. Once that was determined, a leak standard was made. That leak standard was then used to challenge the test and to validate the test to prove that what we were looking for, that falling drop of water, was the limit that we were setting. So all of this data was recorded and kept as part of the validation so that it could be referred to later on. But now that they know 2 cc's of air is the equivalent of a falling drop of water in 30 seconds, they know they can use that calibrated standard to challenge any new product that comes along. Doesn't matter what the volume is, that leak is the leak. So let's just look at questions. See if we're caught up here. Tom is asking, what do you recommend for testing inherently dirty parts? Yeah, you'll want to make sure that when you vent the air out of the test part, it does get into the tester. So if you have air that's going to get from the dirty part into the tester, you'll want to have a filter, or just vent the part externally on the fixture and not through the tester. So either a filter or just vent it externally from the tester would be my answer to that one, Tom. Well, the next slide is going to talk a little bit about volume, and Charlie is going to talk to us a little bit about volume and why volume matters in a leak test.
Hello, guys. So as Don's talking about, we like to show this difference between like a bicycle tire and like a car tire. So say you take a thumbtack and you poke a hole in your car tire, odds are you can still drive to work. You might make it a few days before you even notice that there's a hole in that tire and you're starting to lose pressure. But if you take that same thumbtack and poke a hole in your bicycle tire, you might not make it around the block and you got a flat tire. So this is the same with leak testing. And we always try to get people to, if you can take any amount of volume away, that's going to improve your leak test tremendously. So say you have a real small, piece of plastic that you're testing, small medical part or whatever the part is, and you have your fixture or whatever's holding your part real close to the tester, and you're getting all your results. And then you go home, and that night the maintenance crew comes through your lab, and maybe they see that piece of tubing that you're using and they think they need to replace it. Well, this time they use 2 feet of tubing instead of the 3 inches of tubing you used to have. Now you're going to get different results. You're not going to see as much of a decay. So that's where we go back to, the 2 sizes of your tires. If you have a lot more volume, you're not going to notice that leak as much. It's not going to show up as fast. So we always recommend, if there's any way you can kill volume between the tester and your part, that's going to make your leak testing way more sensitive. You'll see like on fixtures, when we do like chamber tests or whatnot, we'll try to get that fixture as close as we can to the tester. So you take away that volume, in between. The bigger parts, like say you have a part that's, the size of a 55-gallon drum, you fill that whole thing up, you're not going to notice, a real small pinhole in that part like you would in a very small part. And again, that's why we like to show the tire analogy here, because you can actually tell the difference. Trying to go, there was another question, I know a live question we had about volume. Trying to go back to it. For fill time. Do you remember, I thought there was a couple of questions back, Don, that was there something that was about volume as well? I was going to try to touch base on since we're in it.
Michelle's asking if we have a recommendation of a detectable leak rate as a ratio to the volume. I guess, Doug, if you have any thoughts on that, but typically the larger the volume gets, the longer it's going to take to find a leak that's smaller. So if you have a large volume, you'll just need to tune your manufacturing process to make sure you've got enough time for it to detect a leak.
And it's kind of hard to get like an actual ratio that across the board that'll work for you. Everyone's parts are different. And we have some customers that make the exact same part as another customer, and they'll test different. Any given part inside there, if it's a little bit different, say there's a piece of tubing that runs through a hard plastic cassette of some sort. One manufacturer might be using a 40 durometer tube, while the other manufacturer might be using a 70 durometer tube. Now the exact same test running on that, same volume, everything. If one of those tubes is a little bit softer, when you put the pressure in that part, that tube is going to expand. And that goes back to the tester doesn't know the difference whether you have a hole in your part or your part's expanding. Either way, the pressure is dropping inside that part, either from pressure leaking out through a hole or your part's expanding and you have bigger internal volume and you get lower pressure that way. So that's one nice thing, I guess, with the graph on the tester, you can see how your part's actually reacting. Just because you can fill your part up to pressure in 2 seconds and then shut that supply off, that part might expand and grow for another 3 seconds. So if you just fill it for 2 seconds and then jump right into a quick settle time and go to your test time, if that part's still expanding, that's a number that's getting added to your decay value. Now that's not necessarily a bad thing, but you have to remember that if your part's expanding and your decay value number is getting bigger, you still need to make sure you can tell the difference between a good part and a bad part. Now we recommend a 4x difference. That way you can feel safe that you're not ever going to pass a bad part. But some people do gamble that and run that test a little bit faster. The more compliance you can take out of that part in your fill time and settle time, the better chance you can find a very small leak in that part through your test time and not basically be chasing a decay value that's not really there.
Yes, I pulled up this chart again because Doug talked about this one earlier. When Charlie says the 4-to-1, typically you're going to want to adjust your fill and settle time so that when you get to the test, your decay, you have at least your non-leaking part is at least a fourth of what your leaking part is if you're looking at those graphs. So as you can see in Doug's chart here, as he varied the fill time, he was able to broaden that gap and create a bigger difference between a leaking part and a non-leaking part. And obviously, the smaller the volume you have, the more resolution or the more sensitivity you're going to have for finding a leak. So, Doug, did you have anything you wanted to add to that? You're muted, Doug. Still muted.
Sorry, somebody, I was muted by my own host. There are questions being asked about different size leak rates and different volumes. There is no limit on the volume per se of what can be tested. Smaller volumes are very easy because of this. Pressures as well. We run the gambit from very, very small test pressures up to 1,000 PSI. Typically, the higher the pressure you go, the longer the test is going to have to be because of the inherent factors like the thermodynamics. There's other things like safety that come into play when you go to those higher pressures. But then also with the volume, as the volume increases, just like Don says, the length of the test just has to increase. It doesn't mean that we can't test it. It just means we need to take more time because of what Charlie has said, the volume matters, the bicycle tire and the truck tire. Even though you poke the same size hole, the decay is going to show up more readily with the small volume rather than the large volume. And that doesn't mean that it's not leaking. It just means now we have to have more test step time so that we can see that actual decay. Excuse me. So it's not that we can't do it. It's just going to take a little bit longer, and it depends on your cycle time. How many parts do you need to put out per hour? You know, do you have to put out 10,000 garbage can size parts an hour that have a very minuscule leak rate? Well, you're probably going to have multiple test stations to be able to do that. But if you had a tiny little catheter or a tiny little tube set that needed to be tested and you need to do 10,000 an hour, probably, because we'll be able to make a very, very quick test. It'll be very sensitive and we can catch leaks very easily. So it all comes down to time. We can pretty much do anything if you've got the time.
All right. Michelle had asked what the minimum delta pressure is. The tester itself resolves down to 100,000th of a PSI. That's 5 decimal places on a PSI. Obviously, we don't. That's the minimum resolution. We don't like to be down in there. I typically recommend the 3rd and 4th decimal place for your reject limit, so that you've got enough counts that you're not down in the dirt of a signal to noise ratio. Doug, did you have any thoughts on that one?
So yeah, we start getting into the pure numbers of everything. And we do have 5 digits behind the decimal for resolution. And the chipset and sensor that we've chosen to use internally is capable of seeing very, very small changes in pressure. So when we say we recommend that you don't have a reject level that is 0.0001, it's because there are external factors that can affect this. If a operator held one part longer than another before they tested it, you could get a different decay reading. If the air conditioning kicked on, lots of different things can affect it that are external to the actual test. So back in my other slides, we want to have a difference between a good part and a bad part. And typically to get that, we have larger decay numbers that show up on the screen. You can see they're very small decay numbers, 0.1, 0.2. So it's not a difficult thing to achieve, but all the external factors can affect us on that. So
right.
when we talk about the resolution and the accuracy and the repeatability, there are lots of numbers to spout out that mean anything. We've typically found that the decay on the screen has a factor that we can call an accuracy on it, and that's 0.0006 psi. So whatever you see on the screen is going to be plus or minus that value, which is a very, very, very small number, 3 zeros and a 6. We've actually put a safety factor. It's actually 3 zeros and a 3, but it's well beyond what you're going to be using as far as a leak rate. Like Don says, we typically say, good part, bad part should be in that second or third digit for a greater repeatability and greater sensitivity, because of what could happen externally, because of part heating, part cooling, part manipulation. Let's say an operator bumped the part while it was testing and changed the volume. That will all affect the test while it's testing.
So this slide kind of follows up on that question. So how do you increase the sensitivity? So one way to do that is to increase the test pressure. If you put more pressure to it, you're going to find the leaks faster. That is one way to go at it. Another is to lengthen the test time. If you have time in your process to allow for a longer test time, then do it, and you'll get better repeatability, better sensitivity. And the last one is to decrease the volume, if at all possible. Some products, it's possible to use an infill to get air inside, like if it's a valve cover or a molded plastic part that you've got access to. If you can put a filler up inside of it to take up volume, then that will help increase the sensitivity and possibly decrease the cycle time. So those are methods of increasing the sensitivity. I was just seeing here if we missed any questions, because we're nearing the end of our time. The next slide is just to talk about products we've tested. Anyone, Doug or Charlie, do you want to address any of those? There's a few open questions here. Bob had asked about part presence at the end of an arm tooling. Our testers measure pressure or vacuum. So if there is no part, you're going to get a gross leak right away. There are parts available on the market that do part presence as well. So we'd be happy to talk to you about some options. We have reps around the country who have really good options for this as well in their arsenal of products they sell. So Andres was asking about the difference between applying pressure or vacuum to a part, what the difference is. And Doug, I think you and I have talked before about pressure versus vacuum and advantages and disadvantages. Do you want to discuss that?
Sure. So one of the slides that Don had in there was understanding how the part is going to be used. Also is part of that is understanding what's going to happen if you apply pressure or vacuum to your part. If you had a soft part that maybe you were looking for a leak in a wall of the part, and you pull a vacuum on it and the part collapsed onto itself, well, it could seal the manufacturing defect you're looking for and hide it. Where conversely, if you pressurized it and expanded the part, air would leak out of the part and enable you to see that. So you have to understand what the force is going to be doing to your part In some cases, a seal or an O-ring, you might want to test that it will actually do its job. So you might want to push a pressure on it to get it to form into shape. It really depends on what you're going to be doing with your product. If it's used in vacuum, test it in vacuum. If it's going to be used in positive pressure, use it in positive pressure. But there are some things that help out a little by switching from pressure to vacuum. But it really is part dependent. We can discuss this. You can get a hold of us. We can talk about your specific case, because there are a lot of open questions that will have to be. Is the part soft? Is the part hard? Do you have seals? Is there something that's going to move during the test? So there's lots going on.
Just to add a little bit to the vacuum and pressure, like Doug was saying, like we do a lot of work with aerospace companies. Obviously, the end use is going to be in space at a full bar vacuum. Those guys like to run vacuum on everything and try to simulate the end use. Also, we do have, since all of our testers have 100 programs, you can daisy chain pressure decay along with a vacuum decay program as well. And some people do this and do what we call exercising the part. A lot of the catheter manufacturers try to do a vacuum decay on a balloon to see if they can catch a pinhole that way. Well, like Doug was mentioning, when you pull a vacuum on a part, especially like on a catheter balloon that's all inside a sheath, it's already collapsed on itself, and you may mask a leak inside a fold line. You'd never see that. But what some people will do is they'll do a pressure decay test linked with a vacuum decay program and do 4 or 5 of those. And it can be real quick. You can give pressure and then pull vacuum, give pressure, pull vacuum. And what that does is exercises the part. That may get like a catheter balloon inside a sheath to actually move a little bit, so that now you can detect a very small pinhole in a crease that you may not have seen the first time. So just thought I'd add that part in.
Jer is asking how do you know the accuracy of the test at the volumes is an estimate. The accuracy of a leak test really comes down to repeatability, how repeatable the decay results are. If you test the same part, every day, you should get the same result every day, as long as the part's remaining the same. So accuracy of a leak test really comes down to repeatability of the leak test. So I wanted to clarify, accuracy on leak test is repeatability, not necessarily anything else other than just repeatability, because that takes into account all of the effects of the pressure, the physics of the pressure on your part. That's what the accuracy is on a leak test. I think I'm just scanning down the list of questions. I know our time is just about up, but anything else you want to add, Charlie or Doug, before we wrap up here?
If there are any other questions that we don't do, we'll try and answer all these questions. So once this wraps up, but if you have other questions, feel free to give us a call. I'm actually head of technical support. So if you have any questions, feel free to call. Just ask for Doug Harding. I'm extension 106. I can go through any application, give you tips as to maybe possible fill, settle, and test times, as well as help with determining leak rates, or how to get the best out of the tester you have for your application.
We've also been doing some blog posts with different videos answering questions. So if you would like to reach out to any of us with a topic you'd like discussed, we'd be happy to put those answers together on a video that we could share with everybody. We're looking at doing some more of these as well. So yeah, if you've got topics you want to discuss, let us know, and we can get a video, a live show, or eventually an in-person visit back where we can help you understand leak testing and how to apply it in your manufacturing process. I think there's one last question, and I think that that I think will address. Our time is just about up. We got 5 more minutes on our timer here. But one question that came up is, how do I know when to use mass flow versus pressure decay? We're working on a white paper on this because this is a really valid question, but it varies vastly on the part that you're testing and the conditions around it. Mass flow is volume independent, so you can test a part and get a result, and it doesn't matter what the volume is. You'll always know how many cc's your part is flowing or leaking if you're doing a leak test. But there's a lot of other physics involved with that. As we get into larger volumes, it does take longer. Typically, mass flow is a longer process. We have a lot of customers who pressure decay test in under a second. Mass flow typically isn't that fast, but it kind of varies process by process. So we're going to have more information coming on that. We've got a white paper. I think we'll be doing a video on the blog about that as well. So
See, there's a question about temperature. We do have some customers that also test their part. It may come right out of an oven, so it's pretty warm. The biggest thing is if you don't want to test some parts that are warm and some that are not. We have some customers that they have a part that comes right out of the oven, and they test them all at the same temperature and they're warm. And you'll have to run that test long enough so that you can still tell the difference between a good and a bad part. That's the biggest thing, is if sometimes they're warm and sometimes they're not, you're going to see a big difference in a good part that way. So if you can, try to always test them at the same temperature. We also have customers that when they come out of that oven, they'll put them on a rack and let them cool down for, say, 10 minutes or 20 minutes, wherever the case may be. Just keep that same time interval going so that when whatever you validate and get your test parameters set at, if you did that with the part being an ambient temperature, or if you got all those numbers set with the part being 100 degrees, just make sure that you do all your manufacturer testing with the part at that same temperature.
all right. I think our time is just about up, but there's a few more questions we'll be following up with you afterwards, I believe. Our testers, we do a lot of air testing. The majority of what we do is pressure decay leak testing. We do mass flow testing. We do burst testing. We do check valve testing, looking for cracking pressure. There's a lot of different pressure measurements that are capable with our instrument. Coming up on our blog, we'll have a lot of this discussed. We're going to do another one of these and always looking for topics. I think in future, we may talk a little bit more about mass flow and burst testing. But we appreciate your time today. If we haven't addressed any of your questions, or if you'd like to discuss further, our contact information is on our website. Doug and Charlie and I, all of our emails are there, so you can reach out to us directly. We look forward to talking to you. We appreciate your attendance today. We wish you good luck and good health as we go on in the rest of this year. Thank you for joining us.